In this video, I'm going to walk you through the post-lab for Lab 5 Heat of Fusion. In this experiment, you are measuring the change in enthalpy, delta H, for ice as it melts. The first data table is, half of it is information that you measured while you were doing the experiment. So you recorded the initial temperature of the water, and you also recorded the volume of water. You will need to write down the density of water that corresponds to this particular temperature. So it's going to be a slightly different number for everyone. And I think the easiest way to find this information is to just look it up on the internet. So we're just going to look for, let's say that your water was 25.1 degrees. We'll just look for the density of water at different temperatures. Let's go with that. And we're going to get a table of temperatures and the density of water at each one of these temperatures. If you notice here, the density is in units of grams per cubic centimeter. A cubic centimeter is exactly the same thing as a milliliter. So this is density in units of grams per milliliter, which is what we're accustomed to. You may not find your exact temperature on this data table, but you'll find something, just pick the temperature that is closest to yours. So again, what you're doing here is you're looking at the temperature of your water and you're finding the density value that corresponds to that particular temperature. Once you know the density of your water, you will use that to calculate the mass of water. If you recall, the density is the mass of something divided by the volume. And in this situation, we know the density of the water and we know the volume of the water, and we just need to figure out what the mass is. So we're going to rearrange this equation a little bit. The mass is going to be equal to the density times the volume, and we're talking about your density and your volume. You are also going to have a pretty similar data table for the ice. You recorded the mass of the empty beaker. You also recorded the mass of the beaker with the ice. And here you're going to be able to calculate the mass of the ice. That's just going to be the difference between these two numbers. Like maybe your empty beaker was 20 grams and your beaker with ice was 30 grams, which means you have 10 grams of ice. Then in this spot, you're going to calculate the moles of ice. This is going to be a gram to mole conversion. Remember that ice is just water, H2O. So you're going to be using the molecular weight of water, 18 grams per mole. And you're going to set up a conversion that allows you to convert your grams into moles. Now, again, we've got some data that you're going to collect in the lab. You have your initial temperature of water. That is going to be the same number that you've got right here. We just got it in a different table. And you'll allow the experiment to take place, the melting of the ice. And you're going to write down two numbers. You're going to have, you'll have a lot of numerical data. You'll be reporting the absolute lowest temperature that your water reached during the experiment. And you'll also be reporting the final temperature. That's going to be the temperature where you decided to just stop the experiment. Now over here, it's asking you to calculate the maximum difference in temperature for the water. And in the notes or the instructions for question number 3, the maximum change in temperature is the difference between the initial and the lowest temperature. So at some point, the temperature gets low, like it's done all the chemistry that it can do, and then the temperature is going to slowly start rising just due to the water heating itself up because it's sitting at room temperature, which is a little bit warmer than what's going on inside the beaker. So we don't want to record the difference between the initial and final temperature. In this case, we want to record the maximum difference in temperature, which is going to be your difference between the initial and the lowest. So in this case, your maximum, we're just going to say that it's going to be your T. We're going to define it a little differently than we have in the past. T initial minus T max. And the reason that I have you reporting all three of these numbers is because it can be confusing for students. A lot of times students just want to go with the initial and the final temperature, which makes sense because that's how we have defined delta T in the past. But what students have to keep in mind is that the lowest temperature of the water is the true final temperature because this is the point where the experiment stops. This is like a pseudo final temperature. This final just represents the time when you decide to stop collecting data, but it's not necessarily corresponding to the end of the experiment. So it still truly is a final minus initial situation. It is confusing. And so that's why I'm having people write down all three of those numbers. So again, pay attention to the sign, make sure the sign is correct. Think about if the temperature of the water is going up or going down. If the temperature of the water is going up, then that would mean that you have a positive change in temperature. If the temperature of the water is going down, then that would mean you have a negative change in temperature. Over on the next page, you're going to do some enthalpy calculations. So you're going to report the specific heat of water. That is a constant. You need to look that number up if you don't already have it just memorized from using it over and over again. Constant. So go look that number up, the specific heat of water. You have your mass of liquid water, which you calculated right here. So the mass of this water. I'm going to just kind of make a note in here that this is from problem number 1, the mass that you calculated. And then your max, and again, this is just for the liquid. And then you have the maximum temperature change for your water. So that is right here, your maximum temperature change. That is going to be from problem number 3. I'll make a note of that. From problem 3. And then in this last box, you're going to calculate the heat change of the liquid water Q. To do this, you're going to be using your Q-SMAT equation, QSM delta T. We're calculating Q. Your S is right here, your mass is right here, your delta T is right here, and that's going to give you Q in units of joules. Pay attention to the sign in this. Is water losing heat or gaining heat? Think about if water is losing heat versus if water is gaining heat and whether your Q should be positive or negative. Now in problem number 5, you're going to do a pretty similar thing for the ice. So this first is asking you to report the heat change of the solid ice. We're not going to calculate that. We're just going to correlate that to the heat change of the liquid water. Remember that all of the heat that is being lost by the water is being absorbed by the ice. So whatever number you get right here, the number is going to be the same for the heat change for the ice. Again, all of the heat that's being absorbed by the ice is being lost by the water. So if you have, let's just say you end up with 5 right here, 5 joules, which is not what you're going to end up with, you're going to have also 5 joules down here. But again, you need to be paying attention to the sign. So if this is a positive 5 joules, this guy down here needs to be a negative 5 joules, because if heat is being lost by one substance, it's being absorbed by the other, or vice versa. So the number value will be the same, but the sign will be opposite. And I'm going to erase that 5 joules because I don't want anybody to get confused and think that's what it's supposed to be. Next, you're going to calculate or just convert the joules into kilojoules using your conversion factor. 1,000 joules is a kilojoule, so I'll just do that conversion factor. Moles of ice, that is information that you calculated in problem number 2 right here. So you're just going to copy that number, moles of ice from problem 2. And then you are ready to calculate the enthalpy of the fusion for ice. That's going to be calculated by taking the kilojoules and dividing it by the moles. The kilojoules are right here and the moles are right here. So it's just simple plugging it in. Once you get that done, you'll calculate your percent error. The actual value is 6.01. So you're going to plug in your value and the actual value, divide by the actual value, multiply by 100. This gives pretty decent data. If you ended up with a negative number right here, but the number is around 6, like let's say you ended up with negative 5 kilojoules per mole, and instead of positive 6, that almost certainly means that you just screwed a negative sign up somewhere. You can easily go back and fix that and change that. Now, you've got a couple of questions about the experimental procedure itself. This is telling you that the percent error is related to the amount of time that it takes for you to actually start collecting your temperature data. Come up with an explanation for that. Think about what you're actually doing in this experiment. You're melting ice. So it shouldn't be that difficult for you to propose an explanation and explain why time is an important factor. And then, based on that, answer the question number 7 or question number 8. Do you expect your error to decrease? That means, do you expect this number to get more accurate if you work more quickly or work more slowly in lab? Once you get that hypothesis down here, you're going to actually try it out. So let's just say that you decided that your error would decrease if you worked more quickly in lab. You're going to go through and you're going to repeat the whole entire experiment, with the goal of decreasing your error. So we decided that we needed to work quicker. You're going to repeat the experiment and you're going to work as fast as possible. collect all new data. So all of this is exact same data table. You're going to collect all new data and do all new calculations, plug it in all over here and calculate the percent yield of the second experiment. Ideally, your percent yield, ideally your percent error will be lower, that it will have worked. Now, one thing that you need to keep in mind is that this is a simulation software, so sometimes you working faster does not necessarily affect the output of or outcome of the experiment. Like maybe the first time you did the experiment, you worked as fast as the software allowed you to, and maybe, or as slow as it allowed you to, and maybe you can't actually improve. And that's fine. You know, we're just kind of going with the spirit of this. If you were doing it in person, you would have much more control over the timing of the experiment. So don't be so super sad if you do everything you're supposed to do and you calculate your percent error and it hasn't improved, or maybe even it's gotten worse. Don't worry about it. You don't need to repeat it a third time. Just do the math, report your numbers, and that's all you need to do.